Okay, so one of the difficult things about the talks is you hand in an abstract at an early time and you haven't written the talk yet, and you also have to come up with a title. So I came up with this stupid title, How to do a two-phase commit in Akka. And I think it's apparently that was a bit misleading for some people. So it's not about how to implement a two-phase commit in Akka. You don't want to do that, yeah. We'll get back to that later. We'll talk about that topic. But if you read the whole description, it's about the experience moving to reactive from whatever your previous domain was. For me, I've been a Java developer for about 15 years, and I'd say an enterprise Java developer using Java EE a lot. And then you develop a couple of habits, and moving to another platform is a kind of transition. So yesterday in the pub, we came up with another, we tried to think of better titles for the talk. So one was from enterprise, moving to reactive, or something that might have been a valuable experience I had on a previous setup is now a bad habit because it doesn't really transform. For example, you might be very skilled in, say, PostgreSQL and a good data modeler, or what's the word? You're good in defining data models, and then you move to Cassandra. And if you apply the same techniques and you want to define foreign keys and want to do joins and stuff, your Cassandra data model is not going to be good. It's not going to be performant. And this, of course, is the same thing with reactive and the reactive programming. If you apply the same patterns and the same ideas, or maybe even habits you have from sort of straightforward Java EE programming, then you run in a couple of problems, or you'll hit a wall, or there are just things you need to be aware of. So this morning I came up with the final and best title for this talk, and this is the title I would submit now if I was to submit it again. I would say it's a pragmatic view of reactive. I want to look at reactive programming, or at the Reactive Manifesto or whatever, of some reactive stuff, but on a coder level, on a level that I think on, right? Because the first time I saw the Reactive Manifesto, well, you've all probably seen this, I hope. So if you haven't, look it up. It's reactive-manifesto.org. And it's very central to everything we do at TypeSafe. We believe that reactive systems are, well, the future. I don't know how to. I don't know how to say that properly. It's not, it's not our religion, but we think they are a solution to many problems, and we think that that should be the way you build systems today. So if you haven't looked at the Reactive Manifesto, please do. But what might happen to you if you do that is that you see it, that you think the same way that I do. So you see the Reactive Manifesto, and of course you don't want to read all of it because it's a lot of text and you don't have that much time. So you look at the picture, the 4 reactive traits that we've just seen. Responsiveness, elasticity, resilience, and it's all message-driven. And you look at that and you think, okay, well, that's all marketing, right? That's not something that speaks to me as a developer. Every single system vendor would claim that their system is elastic and resilient. If Oracle wants to sell me a WebLogic server, they're going to say, oh yeah, that's super scalable, and it's super, you can have a super cluster set up, all fail-safe, don't worry about that. And IBM will say the same, of course. Anybody, Microsoft, anybody who wants to sell me something, or a software system or an environment, will say, yeah, this is super elastic and super resilient. So it doesn't really distinguish reactive from anything else, right? And then there's the last one, message-driven. It's a bit of a big leap. Right? We have these 3 very abstract traits, and then it's message-driven, right? Okay, so it's just I'm supposed to use Akka apparently, I guess, and that's it. So I think on a developer level, these are not. I don't know, the questions we face in the development work, or questions we get from users, are sort of in a different problem space. We get questions like these, like, how do I deploy my stuff? Do I still build a wall? Do I run it in an application server or servlet container? Oops, that was the wrong button. How do I do database connectivity now in an asynchronous setup? Well, I use this library and it doesn't work anymore. It doesn't do what I expected. It might be because it uses ThreadLocals. A lot of people have experienced that with logging, for example. You used to use the map diagnostic context, and now suddenly it doesn't really work anymore like you expected. Or you use, I don't know, Spring Security or other things. A lot of libraries store stuff in ThreadLocals, and we're going to talk about that. And yeah, of course, the shiny thingy, how do I do sort of something like my customer says it's a requirement that we have this distributed transaction there, and now it's all async and messaging. I have no idea how that sort of relates. So let's look at these things. I think the topics that are actually interesting there are the concurrency model that's underlying all this. How do we do I/O? That would include database I/O. How do we deal with the whole distributed situation? Because we don't want to build systems with a single point of failure or a single point of contention. And then how do we deploy all that stuff? So I present to you the Pragmatic Reactive Manifesto. Don't tell Jonas Bonnet about this. He's probably going to kill me. But I say from a pragmatist point of view, the reactive traits you want to look at, or the traits you want to look at in your code, if you will, are sub-thread level concurrency, task level concurrency. You have asynchronous I/O. You have a true distribution. You don't have single points of contention or single points of failure, or a single central database or whatever. And you're running without an application server. This used to say containerless because they're called servlet containers, but now if I say containerless, people think I'm saying something against Docker or something. It's not about containerization in Docker, it's about servlet containers and application servers. So, over the next couple of minutes, we're going to look at these four traits. Yeah. So on the JVM, our basic concurrency model is the threads, right? It's a multi-threaded environment, and the JVM threads map to native threads, and that at the time seemed a pretty good idea. Before that, there was multi-processing, and starting a new process for anything you want to do in parallel is rather heavyweight, and also you have a communication problem. You need inter-process communication to exchange data between these processes. So people thought, oh, let's just use threading, and that's going to be super lightweight, and also they can just share the same address space, they can just share the same memory, and can super easily communicate. Yeah, that seemed a good idea at the time. By now, people don't believe that anymore. Threads, and this is not some Scala versus Java thing. This is actually somebody from Oracle who says threads are the past. We need to look beyond that, and they are. Oh yeah, this is about the programmer. Yeah. Okay, not about the efficiency, but also it's inefficient. It's heavyweight, and the shared memory thing actually makes concurrent programming rather difficult. Right? You end up with something interwoven like this, and it's always sort of, you start up nicely, but every time I get this out of the pocket, my earbuds, it's all intertwinkled and complicated. And this is what happens to multi-threaded programs as well. So threads are actually not that efficient. The memory consumption is pretty high, especially if we talk about JVM threads. I think the default stack size is a megabyte on a 64-bit JVM. So for each thread you start, you have at least 1 megabyte. If you run 10,000, which is the kind of number where it becomes interesting, it's at least 10 gigs that are gone there for that. And then you have this whole switching thing, right? In the modern processor architecture, you have the non-uniform memory access where you have the different cache layers on your processor. And you really want to stick the thread to the core. Well, the ideal situation is where one thread just runs through on one core all the time and has all his working set in on the processor cache. Whenever this thread blocks, it's going to be kicked out by the system scheduler, and it's going to lose all its context, and the switching is going on. And of course, that won't kill you if it's about 20 or 30 threads, but if it's about 20 or 30,000, that becomes an issue, as does the memory. And the shared memory model, of course, has its problem because you need to synchronize on that somehow. Either you have race conditions because you don't, and then you see, oh, this doesn't work, I have timing issues, I have weird stuff, so I need to lock on that. Locks lead to possibly deadlocks, or at least they lead to contention, like you have to wait to get lock. So threads are not efficient anymore on modern hardware and on the scale we're talking about, and they're also not really a smart programming model in terms of, making it easy for you to write your program correctly in a multi-threaded environment. So what we do is we want concurrency on an even lighter level, on a sub-thread level, or a lot of people say task level concurrency as a generic term for that. and you want a share nothing approach, where you send immutable values around, so you don't have to worry about synchronization and locks. And yeah, well, you want to optimize the number of your threads. You want to deal with a small number of threads that corresponds not to the number of tasks you have, but to the resources you have available. There's no point in having 10,000 threads if you have 8 cores. You can't run more than 8 in parallel anyway. So it's really only useful to sort of, if you will never block, if all your work is totally CPU bound, say, then why have more than 8 threads? That's what you can do in parallel. That's what you should have. And then the threads can just run each on its core, and all is good. There are a couple of ways to approach this, or there are a couple of competing, if you will, models. Like the lowest, or the smallest step would be to keep the same programming model, a sort of synchronized sequential approach, but still going sub-thread level. This is what Go does in Go routines, but that's of course not on the JVM. On the JVM, I think the closest implementation to that would be fibers, because our fibers. But as I said, you still have basically the same programming model, and you'll still usually share variables and have the whole locking synchronization thing. A step beyond that, to a different programming model, would be an event loop system, like Vertex or Reactor, where you sort of put events in an event loop, and they work on that. And of course, what I think is the most powerful system, actors. Actors sort of give you even more flexibility, because you can also sort of address actors directly. You have the whole routing thing that Akka gives you. Plus, they have this whole resilient supervision thing. And from a dispatch point of view, it's also a bit more flexible. In a traditional event loop system, you really have one main thread for the event. While in Akka and Play, we have an N to M mapping, not a 1 to M, where you have sort of like one thread working on N tasks, but you have M threads working on N tasks. We're going to look at that. Well, let's look at a maybe more specific example, or real-world example, or real-world problem, whatever. You build a web application and you have incoming HTTP requests. So if you've been a Java programmer and you've done servlet programming or JSF or Wicked or anything that runs on the servlet API, Spring MVC, the model, how your code is going to be executed, is basically going to be like this. For each thread that comes in, or for each request that comes in, it's going to pick a thread from the pool, and then this thread is going to stick to this request. They're going to be married and going to sort of live their life happily ever after, and once the request is processed in a rather synchronous manner, then the thread is returned to the pool. So this is not supposed to be a sequence of things. This is like a snapshot in time, right? We look at our system and the number of threads there, what they do, and if we have 10 concurrent requests in a traditional thread per request model, 10 threads are going to be used, which is that gives you a lot of simplicity in a way, because then, of course, you can rely on this sequential execution of the code in your thread, in terms of you can use a ThreadLocal, for example. You can put, and that's why all these Java libraries do that. You can just put some context in your ThreadLocal, and you know, okay, this is going to be my thread. I'm going to run on this thread, and I can clear it up at the end and keep this context all through my call stack. If you go to a sub-thread level concurrency, though, that doesn't work anymore. The way, so if you now take a snapshot, well, this of course is a bit simplified, because you get the requests in and actions are created and then put in a queue and then workers work on them. But if you just look at the threads and which requests these threads might work on, you'll definitely have some sharing there. So you don't have this thread per request model, you have n requests for m threads. In this case, just 3 threads are used, but they're working still on 10 requests. So you see, these would at least be sharing thread locals. And of course, we also go towards an more asynchronous execution. We're going to use futures and go to other execution contexts, so this whole thread local thing will not work anymore. So what are the consequences of this when we actually go? Well, if you use Akka or Play, you're switching to a different concurrency model. I think we're not explicit enough about this in the documentation, especially in the Play documentation. Some people believe if they don't use async with Play, then it's like thread per request and all synchronous. Play is asynchronous by default and will not attach a thread to the request. That will all be queued, and a pool that you define will work on that. So you have to be aware that you switch to a different concurrency model, and something like ThreadLocal really becomes an anti-pattern. You can still, well, you have to do a lot of extra work to still use it. If you want to use it, if you still want to use the map diagnostic context, you have to sort of patch your the execution context to hand over the context in an async manner to the other threads. Sort of the thread that passes off the execution has to hand it over to another thread, and it becomes even more complicated in in real distribution with Akka. Then you have to sort of add an envelope to the message and push the context over with the message and stuff like that. So I really advise you to avoid anything with ThreadLocals. There are, of course, other approaches then to get some async logging or some async information. So carry your context across async boundaries. TypeSafe is working on something that's going to be provided in Akka and Play or in the TypeSafe Reactive platform. And there was a talk by on&nbsp yesterday that they use bytecode instrumentation to do all this sort of nitty-gritty stuff to pass over the context and things like that. So this is how you could handle that. So that would need extra work. Okay, so don't use ThreadLocals. That's like the basic learning for that. Pragmatic learnings, first version. You will be using sub-thread level concurrency anyway, accept it, and see the consequences. Async IO. So if you want to live with less threads, if you want to use less threads, it becomes super reasonable to use asynchronous IO. Asynchronous IO became super popular with Node.js. Node.js was very efficient and could handle like 10,000 concurrent requests on a single core CPU or whatever, and with a single thread, which was quite impressive, I think, at the time. And the way they did that is that they leveraged the operating system facilities that allows you to load off actually all the I/O work from the CPU. It will use the I/O controllers to run its I/O threads, but it will not use up your main threads, your CPU core threads, if you will. So now, if you're used to using blocking I/O from the Java world, you just use your old Java I/O file or whatever, and you remember the situation. Now we have our M threads, and each of these threads is responsible for N requests, right? What happens if we block one of these threads? In a thread per request model, if we block one of the threads, this thread is responsible for one request. So this one request, the thread there is going to be blocked, it's going to wait, and is going to have the problem, if you will. But here, the number of requests that we handle with a single thread can become pretty big. So the extreme example would be to have just one thread. You have one event loop thread that works on these things. If you block this thread, everything comes to a halt. So if you go sub-thread level, you don't want to block your threads on I/O. Of course, if you have CPU pound work that has to be done, then that has to be done. But for I/O, you really don't have to block. You can use asynchronous networking. There are libraries available. You can use asynchronous file I/O, and that's really what you should do to sort of keep your thread pool ready for the incoming requests and for the CPU bound work. Now you say, but what about this? I need to do database access, right? I want to use a relational database. I need to use JDBC. For a relational database, or I do not know, well, there's no asynchronous JDBC right now. If you use JDBC, that's going to be a blocking call. So how do we handle this in a pragmatic fashion? The non-pragmatic way would be don't do it. Use something else, use Cassandra or MongoDB or whatever, but we want to be pragmatic and we say, okay, it's going to happen, or that should be possible. We want to use a relational database, just as we did before in the past. So isolate your threads. What you can do, and you can do that very nicely in Play and Akka, is to define different dispatchers for different tasks. So you can have your main dispatcher for the incoming request, and so for the CPU bound work, as we had before. And you just sort of reserve a different thread pool for the blocking I/O. And conveniently, Slick 3 will actually do that for you. Slick will give you asynchronous API on top of JDBC. And internally, it's basically how it works. It uses its own execution context and will use a number of threads that you can, of course, configure independently of the rest of your application. So what we've learned so far is you'll be using sub-ThreadLocal anyway, and you don't want to use blocking I/O. Use non-blocking I/O, and if you really can't, if you really have to do a blocking call because you want to use JDBC, then just isolate that and use a separate thread pool. Right, and now to the sort of to the title topic of the talk. What if we go beyond that? What if we don't only have a database access, like a JDBC call where we do a select, or as we did in the previous example? Here, we actually have two transactional systems. We have a message queue and a database. And this is within one transaction, which in this case, I think this is code, some Spring example code in Java, obviously. That makes it pretty easy, right? I have to define a transaction manager somewhere, but once I have this, if I have a transaction manager that's capable of handling distributed transactions, this is all I have to do to have this all or nothing approach. So in an asynchronous system where I actually want to avoid blocking I/O even, how could I possibly do something like this? And the answer, of course, is indeed you don't really want to, but well, being pragmatic, if my requirement is all or nothing, how do I handle that? So there's a bit of a local color here. This is German. I don't know the English equivalent for that, but I like this. These three steps: avoid, separate. So this is about trash, household trash. You should avoid it. If you can't avoid it, separate it. If you've nicely separated, you can recycle it. I'm not saying distributed transactions are trash, but I'm saying it's interesting to look at these three steps: avoiding, separation, and possibly maybe, well, if you really can't do anything else, recycling. Avoiding. So this example is actually, in this context, it's actually, I didn't even, it's just something I copied from the internet, but also I've seen this in real-world projects, exactly this combination, the message queue and the database access. And, well, distributed transactions or two-phase commit or what have you, what is it about? It's really about all or nothing, right? You don't want a two-phase commit. What you want is you want this all or nothing guarantee. I have two separate actions. I want to write in database A and database B or whatever, and you want it either all to happen or nothing at all. Now, if you look at this example, this is actually not even that. It's not even all or nothing, because you don't know what's on the receiving end of the queue, right? This is it doesn't give you any guarantees if the data you put in the message queue is going to be processed correctly on the other end. All it guarantees you is that your local transaction has worked. Or I consider in this case, I consider this database transaction, I'm going to call this the local one. It's like your local database. And then there's some other system somewhere else where you want to send a message to. So this is really not all or nothing. I think this is the first way or the first step you should take in approaching this. If in your in working out the requirements or talking about the user stories or whatever, you have this all or nothing situation, and they say, oh yeah, we need to insert it in the database and we have to send it to this other system. You really have to challenge that and have to say, is this really an all or nothing situation? Or in this case, I would call that reconciliation, right? You want to insert it in your database, and you just want to make sure that another system reconciles with that and takes up these changes as well. So I think in this particular case, if you have this combination of a local database and a messaging queue, I would advise to really separate that and to do the operation in a local database in a way that you mark if it has been transferred to the other system or not. And then you can easily have a completely different process that does the reconciliation and makes sure that the data is going to be sent to the other system, but completely asynchronously. So my advice would be first to try to avoid it, try to identify if it's really necessary here, the all or nothing, or if it's maybe just it's because it seemed easy to do it, and don't do it. But of course, we want to be pragmatic and not principled. So in a pragmatic fashion, somebody could say, oh yeah, I still want to be able to do it, or I might still have this requirement. And now it becomes a bit more, I guess it gets a bit more work. But the basic idea is you can achieve the same effect. You can get the all or nothing also with asynchronous messaging. And I think for me, sort of the principal explanation is from this paper, or this is like a very general consideration how to achieve that. This is by Pat Helland, Life Beyond Distributed Transactions, and it's also a very funny paper because it's a very opinionated, well, funny. You know, geek funny. It's not super funny, but it's he's very opinionated. Like if you look at slides from him, he's like, grown-ups don't use distributed transactions, and distributed transactions don't scale. Don't even try to argue with that, just believe that. And well, yeah, that might be also worth considering. So the two-phase commit with a transaction coordinator is not good in a distributed system, or maybe it's something we should sort of make ourselves aware of first. Why do you even not want the distributed transaction in a traditional sense? Well, if you think of the reactive traits, right, we want to be scalable or elastic and resilient, and this whole concept of the synchronous two-phase commit is really not made for that. If you look, I think even in the Oracle transaction manager documentation, it says something funny about the commit point should be a system with low latency and always available or something like that. Because that will really break, well, if one of in any step, well, it's also a multi-phased process, right? You get the prepare calls to each of the parties that's involved in the distributed transaction, and then you have the actual commits or rollbacks. And at each point, or at any point in the sequence, of course, we should be, well, it doesn't really account for the ability for the systems to fail. And of course, the latency will hold you back as well. So it's a natural point of contention and failure. And so, yeah, it was actually, I think it was more an observation than a principled thought to say we see when we build highly scalable systems that people just don't use that. So I said, you can, in principle, replace any two-phase commit with messaging. It's, well, of course, it's not that easy. You can't just say, okay, I'm just going to use an actor and send some messages, and that's going to be like a two-phase commit. You need some restrictions there. You need to do some additional work. Well, you must make sure that the message arrives at your destination. So you need at least once delivery. Right? It's not, the standard. If you just use Akka without persistence, just a memory, you have the at most once delivery, right? You send a message, and it might, you are sure it's not going to arrive more than once. But that's not a good guarantee for a sort of, to model an all or nothing scenario. What you want really is at least once delivery, and you can't guarantee the message order, right? Or multiple delivery. You might have multiple deliveries of messages. So you need to make your messages idempotent. Or you have to handle it somehow. This is a very compact way of saying it, making the messages idempotent. You have to be able to handle multiple deliveries of messages and out-of-order delivery of messages. And lastly, well, you have to have some rollback ability. You have to have an idea of a tentative operation. I think the textbook example is a hotel reservation. In this paper. So the idea is you send out this request. You know it's going to get there somewhere, sometime. It's at least once delivery, and say I want to book this hotel room. And now you have to have you have to have the sort of the concept of this being tentative. You say, okay, I reserve this, but this is going to be valid for a certain time until it's acknowledged, or it's reversible, right? So that either it's going to be acknowledged at some point in time, right? So, of course, the way you communicate with messages is that you send a message and you get an acknowledgement back. Either it's going to be acknowledged at a certain point in time, or I have to reverse that, right? So it's not, I don't have it like a simple flip switch solution. Like this is the code, how you do, this is the distributed transaction. Now you just sort of automatically transfer the code and send some messages, and now you have this in an asynchronous distributed manner. It will actually affect your modeling. You will actually have to think about the messages you do and about your process. But it should be possible. Now, yeah, I would stop there and say, okay, this is how you do two-phase commit in Akka, or how you do all or nothing in Akka. Maybe, okay, but now maybe some of you are saying this is, are going to say, but that's not pragmatic enough. That's a bit like very principled. You say, oh, any two-phase commit can be replaced by asynchronous messaging and at least once delivery and idempotent messages. So a real-world I think a pragmatic approach, how it's actually been done in the real world, would be the saga pattern. In the saga pattern, you start a story or you start a saga, and each of your each of the steps, each of your single commits has a counterpart that will reverse the operation, right? So, say the T1, T2, T3 are transactions, and the C boxes here are compensating actions. So you start a saga, and you say, book my hotel room, reserve the car, as it happens. There will be an example right here, a stolen one, I must admit. So the transaction will be to book the hotel, and the compensating action will be to cancel the hotel. You book the car, you cancel the car. You book the flight, you cancel the flight. Now this is not built in Akka. I haven't even seen a reference implementation of that in Akka so far. But it's been done in other contexts. And well, what you have to do is you have to have a saga execution coordinator. So you have to have somebody who takes care of recording these actions, these transactions, and making sure that, well, either at the end to say, okay, this saga has been successfully completed, or make sure that the compensating actions are executed, right? And so it needs some durable log, the saga log, and also here, well, it's kind of you'll find the ideas from the principled approach back in here. So having a compensating action sort of corresponds to the idea of having a tentative action, right? Booking the hotel is tentative in the sense of it's reversible. I can have a compensating action and that will sort of would take this back, at least until the saga is completed. And you need the at least once messaging and the ability to handle multiple messages or the out of order messages in the compensation phase. Well, you must make sure, or you must have the guarantee that the compensation message will be delivered at least once. Otherwise, you can't guarantee the all or nothing approach. So, what we would learn from this, distributed transactions. I'm going way too fast. I'm almost through here, and we still have so much time left. Well, we'll see. Distributed transactions are a source of contention and of failure, so you should definitely avoid distributed transactions, and many people would say so. Local transactions are fine. I think the saga pattern is actually a good pragmatic solution for having an all or nothing approach in a distributed world. Also looking a bit ahead, we see now a lot of systems that don't use the database or don't have the central database with mutable state at all anymore, but use a different approach like event sourcing. And that, of course, a lot of these all or nothing problems, they stem from the fact that you have the idea of having a sort of this mutable data store where you have the single source of truth at any point in time. If you go to a different approach, well, from a scalability and flexibility point of view, I think this whole event sourcing thing corresponds very nicely with reactive applications. And also, if you've seen the keynote by Jonas Bonner, this whole, it's also a very principled question if you really want this, or if it's a meaningful idea to have a global truth at a certain point in time. What is the present? What is now? I think is if you think of of the present being a consequence of events, things like that. I think this questions the whole concept of having a central global truth data store. So this goes a bit beyond the pragmatic thing maybe, but I think the good news is that it's probably going to be sort of, we're going to build systems differently anyway, and we don't worry so much about two-phase commits and stuff like that anymore then. So our pragmatic reactive learnings, we're going to use sub-level, sub-thread concurrency, we're going to use asynchronous IO, and do not use distributed transactions. Oh, the last thing about the distributed transactions I didn't even mention. So I said there were three, it would be a layered approach, a three-layer approach. Try to avoid them, question the requirements, see if it really is an all or nothing, or if it's just some system reconciliation. If you can't do that, then you can refactor it. If you have idempotent messages and a at least once delivery, which Akka persistence would give you, and have some concept of tentative operations, then you can achieve the same all or nothing in a distributed fashion, or you can use, as a more specific example, you could use the Saga pattern to achieve that. Of course, the third option would be just to leave it as it is. That's you can isolate this just like you isolate the synchronous I/O, right? You could sort of put this on a different thread pool, and you could put your whatever you want to process in a queue, and have this sort of have this process asynchronously from the rest of your application or whatever. But of course, you're going to pay a price for that. You're going to you will not achieve the same resilience or the same scalability, elasticity as you would with a refactored solution. But that's always a trade-off, right? If you say, okay, for some reason this is real, I really have this kind of acid consistency, a strong consistency requirement, and I need this this two-phase commit there, then it's always a possibility to sort of live with that and have the trade-off availability for consistency in this case. Okay. So as a little, these were actually sort of the main points I wanted to get across. As a little bonus, another question we often get is about deployment, really. Sort of how, if I build an Akka application or Play application, can I deploy that on my whatever Java Enterprise or my Java Enterprise Edition server, or on my Tomcat or Jetty or whatever. So it's not really related to the whole concurrency and asynchronous idea, but I would argue that reactive applications would be standalone applications or containerless applications. I really like this talk a year ago. I think application servers are dead, and there's he created a lot of context around that. And also, my former colleague James Ward said, if you still think you want to use containers or like service containers to put your services in, then you probably missed the memo. Nobody's doing that anymore. Everybody's like Dockerizing the stuff and building little standalone stuff. So why the backslash? The backlash against application servers. The idea of the application server. Well, first of all, from a technical point of view, if you use a Java EE application server, you're going to use the Servlet API. The Servlet API bears some recent additions that haven't really become popular so far, is a synchronous API, right? You get in the request, and then the idea is to process it synchronously, and blocking and all that stuff, as we saw with the thread per request model. The Servlet API is built for the thread per request model, so we don't want that. So this is a technical reason. It's a low-level technical reason not to use them, and another reason is sort of the benefit we get from the application server. It adds some complexity, right? I have to buy it, I have to install it, I have to sort of operate it. And what does it give me? It gives me some APIs. And the idea is to have sort of a container where I can put in a number of services. I put in a number of wars for different applications. Nobody does that in reality, though. The value of isolation, or in all the projects I know at least, the value of isolating your systems and making sure that a crash of one will not affect the others, or a sort of an immense load on the other one will not affect the others, is much higher. The value of that is much higher than the value of being able to sort of deploy a couple of applications on one server. So what people do is they take one application per application server instance. But you'd rather start a couple of Tomcats with one application in it than one Tomcat with 10 applications in it. If you only deploy one application per Tomcat, well, Tomcat now just being an example, then what Tomcat really becomes is just a library that you add to your application, right? It's just sort of a way of delivering that. You sort of, instead of wrapping it, instead of not wrapping it together and just building a war and putting it somewhere, then you could sort of wrap it together and just build one binary out of it. This is what Spring Boot does, right? Spring Boot just sort of gives you a standalone jar that you can run, and it just puts the Tomcat or the Jetty or the Undertow what you want to have in there. Well, if it's just a library, why not just use a library? Why use the application server, right? Then you can just use an HTTP library, just like we do in Play, and you sort of you get the better of it. The sort of, there might be some ops convenience. So from the operations point of view, people might like that. I know of a company that uses Akka, and they don't use Tomcat at all, but they still do. Well, they still sort of, they use the Tomcat, they still deploy it as a WAR file or so, and it has to run in a Tomcat. They just use the servlet context, or what it's called, that's the fired up at the beginning to start up their Akka actor system and stuff, and then nothing else of the Tomcat is used, but they have to because the ops people require them to. Everything they do has to run in the Tomcat. So there's some ops convenience maybe related to this thing, but there are other tools, I think, nowadays that you can use to conveniently deploy small services and operate them. I don't want to mention Conductor, but that would be one of them. So to wrap up our pragmatic learnings, you're going to be sub-thread level. You want to use asynchronous I/O. If you really, really can't, at least isolate your stuff if you have the synchronous I/O. You don't want to use distributed transactionals. They're fragile, they're points of contention. You want to use, if you need all or nothing, you want to use a different model. You want to use something like the Saga pattern, or Saga pattern based on messaging and asynchronous back and forth. And you don't want to use an application server. You don't want to sort of deploy there. Right. If you want to have a checklist for your code, so going back to the pragmatic, this is really sort of what I wished for at some point in time. So I want to sort of look at stuff and want to be quickly able to see, is this sort of what I thought I should build or not? So all the other way around, the positive list, the sort of positive checklist would be just the 4 things I just mentioned. I'm just not going to repeat them. Now, in the beginning, it may have sounded as if I didn't like the Reactive Manifesto, because I said the Reactive Manifesto is just marketing, and I think we should have the Pragmatic Reactive Manifesto. That's not actually the case. If you think about what we talked about here, we really only talked about this part, about the scalability or elasticity part, right? I think to be elastic, these 4 things I mentioned are things you have to do. But so what we did, or if you look at sort of the pragmatic part, it's not an alternative, or it doesn't cover the same grounds as the Reactive Manifesto. I'm just saying, to be more sort of from a pragmatic point of view, if you want to talk about elastic, what does it actually mean? I think these 4 traits that I mentioned would be the answer. And talking about the big leap between the 3 sort of very conceptual things and the message-driven at the bottom. If you actually use Akka and thereby use a message-driven architecture, all these things I mentioned will actually come to you, right? You will automatically, you will work with actors, so you will automatically have the sub-thread level concurrency. You will use asynchronous I/O most possibly with Akka, or at least isolated and separate actors with separate dispatchers, whatever. And you will probably build a truly distributed system and not deploy it in an application server. So what I'm trying to say is, I think after giving it some more thought, I actually think the Reactive Manifesto is great, and I just try to fill in a gap there and try to explain why message-driven leads to elastic systems and what this would look like sort of in a very pragmatic fashion. And that was all I have to say for today. I have the portable mic, so if you have questions, then you have to ask them without a microphone, and I'm just going to repeat them for everybody to hear. Yeah, there's a question here.
I'm a bit interested in this, how to replace ThreadLocal if you want to have some kind of context for your request handling or something like that.
Yeah, so the question is, if you can't use ThreadLocal, but you want to sort of move context around, there are, for logging, so one possibility is to explicitly, I shouldn't say explicitly, you can pass your context around, right? Also, Play does that internally by using, well, it's not explicitly because it uses implicit parameters. I would say you could use an implicit parameter to just sort of, have the dirt in your code, not to introduce too much boilerplate. And I personally like that. I personally like the idea of passing the context down the call stack. For me, ThreadLocal is a bit like having a global variable, right? It's not global, obviously, it's thread scoped, but it's a bit, out of the scope you usually think in terms of programming, your lexical scope, obviously. Other approaches would be to put some work in to automate this, I'm going to put the slides on SlideShare, and I'm going to put some links in there as well. So there's some, I think, rather popular blog posts about how to use map diagnostic logging context, for example, in SL4J with Play and Akka, for example, where they just built their own execution context, and there's like a handover method, I think, in the execution context where you just in the prepare, you kind of take the context from the one, and then when the control goes, or when the switch is done, the async passover is done to the other thread, it would get that context. And or as I said, but that's of course also like rather logging specific, not something you would use in your application internally. You could use tools like Kamon. Never use bytecode instrumentation. Kamon, Kamon.io. It's for logging or metrics retrieval from your application. That will do quite a bit of aspect J weaving with your code and make sure that the stuff is passed around. That would be things you want to maybe see in your logs or in however you collect your metrics. I think if it's about context you actually use from within your application, like business context, I would advise to use parameters and just pass them around. But I'm also open for suggestions from other developers there. A question here in the middle. Yeah, well, I think people use futures a lot as well, right? But if you use the question was, the Reactive Manifesto puts a lot of emphasis on being message-driven to being reactive. And what about futures? Right? We also have futures. I didn't even mention that as a model. Well, there are two things about futures. Futures futures are a better abstraction on top of threads, right? They're sort of a nice way to work with threads, but you don't really get a sub-thread level dispatch. You don't sort of get another dispatcher that rotates your tasks, if you will, or sort of goes through the task with a thread. It would be from the granularity, it would be the same level as a thread. And the future poses the question, how do you work if you have mutable state in your application? This is, in many applications, that's just the case. When you can, or people build, I think Stu Hood from Twitter had this talk about the history of how Twitter built the application with Scala. They don't use Akka at all, for example. And you could claim that Twitter is rather elastic and that kind of works. And they use futures, but they try to make all the services completely stateless, and everything which is state is put in some cache somehow, and retrieved, of course, from the cache. So if your application is completely stateless, I think you're going to be fine with futures. Actors are a good way to encapsulate state in a reactive application. Yeah, a question from Carl.
Don't you often defeat the transaction by using cache
Yeah, but that's probably using caching. Oh, so the question was, I'm not sure if I 100% understood it. So if you work with transactions and you have a transactional context, but you also use caching, and possibly without knowing, and that kind of defeats the whole transaction thing. Yeah. But I would think that would be, yeah. So are you saying, though, that if you use JPA and the second level cache, and you have a transactional write to the database, it might only be written through the cache and not written through to the database? I think that's not how it should work, actually. I think it should be written through, or the transaction should not be completed before it's written through to the database. Oh, and then you don't really have the strong consistency that you think you have. Or you don't have to. Yeah, so that would be a good point for sort of questioning strong consistency in general, and saying also, even if you use the traditional approach and you think, oh yeah, we do this because we cannot afford eventual consistency, we have to have strong consistency all the time. Maybe you just don't know it, and you don't have it already because your distributed cache is just not propagating the changes properly or fast enough or whatever. Right, they're making funny symbols here. I'm just going to ignore it if there are more questions. Then, well, I'm around anyway, so I'm going to hang out in some other talks and at the TypeSafe booth. And so, if you have other questions, you can just find me and talk to me. And enjoy the rest of the conference.